Hi, everyone. So in this episode, we are going to review what we know about free energy and kinetics and equilibrium from your general chemistry class. And as we do this, we're going to talk about reaction rate and reaction equilibrium. So the big idea here is that enzymes alter the reaction rate, but not the chemical equilibrium. So as we talk about reaction rate, we're talking about the kinetics. As we talk about the reaction equilibrium, we're really talking about those thermodynamics. So the reaction equilibrium is determined by the free energy difference between the products and the reactants. And if you remember, we talked about the equilibrium constant K. So at its simplest, K was products over reactants at equilibrium. We'll talk about that some more. And if you remember, if K was more than 1, we had a product favored. We're making a lot of products, so product favored. But if K was less than 1, then it was reactant favored. It did not, the equilibrium had a lot more reactants left than going towards products. So let's look at an example reaction. Just a generic A plus B goes to C plus D. If I was going to write my K expression, my equilibrium constant, it's products, so C times D over reactants. And each of them is raised to its coefficient in the balanced chemical equation. Here they're all 1. But if I had had like a 2 here, then this would be squared. But I'm going to erase those because that's not what this equation was. Okay, when we looked at these in general chemistry, we looked at some charts that looked like this. We had free energy on the left. We have our mixture changing as we go to the right. And so we have reactants. At the left, it's all reactants, and at the right, it's all products. And we looked at these graphs, whoops, didn't mean to do that, but that works, that started. So this is showing you the free energy for each mixture, each component. So when the free energy is almost all reactants, we're right in here somewhere. It's still got pretty high free energy when our mixture is almost all reactants. As we move towards product, we see our free energy getting lower until finally we hit this point down here. And let's mark that point because that's our lowest free energy. And we're going to say delta G is 0. So if you remember, we talked a lot about the standard Gibbs free energy change. That is here, going from all reactants to all products, okay? Delta G can vary depending on where we are along the reaction. We'll look at our equation for that in a minute. But really, it's the difference between where we are and equilibrium, that lowest energy point. So when we're at equilibrium, there's no difference, and it's 0. This would be an example of a spontaneous reaction, because I can see that my standard Gibbs free energy change would be less than 0. It'd be products minus reactants. The products are lower, so it'd be negative. Okay, so we would have called that spontaneous, or now that we're talking about equilibrium, we would have said product favored. It's going to go far towards product. That minimum is close to the products. Or, in terms we've used now, exergonic, right? It's net giving off energy. We can look at the case where, so we've still got our mixture going to the right. We've got our Gibbs free energy, but now our reactants are lower than our products. We're going to see the same curve, but now it'll be reactant favored. that delta G equals 0, that equilibrium point is closer to the reactant mixture. Okay, we are still going to see this standard Gibbs free energy change, delta G standard, right? But now it's going to be positive. Delta G is going to be standard is more than 0, right? It's going to be reactant favored. When we were doing thermo, we would have said non-spontaneous. Doesn't mean it doesn't go towards products at all, just not a lot, okay? Or now we could talk about the fact that net, it has to absorb energy. Okay, so what we see here is that our free energy changes depending on the mixture. Okay? And we have an equation that relates that. So we looked at, when we were talking about thermo, the fact that the Gibbs free energy for whatever our actual mix of reactants and products is equal to the standard, going from all reactants to all products, plus this correction factor. So this right here would not be the equilibrium concentrations necessarily. That was what we called Q. So if you remember, I'm going to go back up here for a second. K is this at equilibrium. So these are the equilibrium concentrations. But we can do the same calculation and call it Q with whatever concentrations we happen to have. So this whole thing is the correction factor. It says, where are we along that curve? So how much do we need to correct our delta G standard to get our actual delta G value? We want to add a little something. So we know that the standard, we talked about 1 molar concentrations. We talked about 25 degrees Celsius. Okay, we talked about 1 atmosphere. But look right here. Now we're also going to specify pH. Okay, because pH is so important in our biochemical system. So we need to specify that. Notice that that means that our H plus concentration is not 1 molar, right? So at standard conditions, everything else would be 1 molar, but H plus would be that 1 times 10 to the negative 7. So I'm going to come in here and fix that right here. If we want to do all of those values, we're going to add that in. And then remember that at equilibrium, delta G is 0. And this whole thing would be equilibrium values, so we could call it K. So I get 0 is delta G standard plus RT natural log K. Or I can solve that and find that my standard Gibbs free energy change is negative RT natural log of K. And I'm going to stick that here to remind us that this is at pH of 7. Notice that this is the relationship right here between our Gibbs free energy and our equilibrium mixture, and nowhere in there does it talk about a catalyst. Okay, the catalyst does not change these. All the catalyst is going to change the kinetics, the speed of the reaction. All right, a little bit more review to alleviate some confusion, hopefully. So we have 2 different graphs. We have that one we just drew where we had the mixture going this way. We have Gibbs free energy. We have our reactants. We have our products. And we have some curve like this. The other one we're going to draw a whole lot is here, but now I'm going to call this the reaction coordinate. Okay. And if I have those same reactants and those same products, they'll be at the same level. But now we see this graph. And so I want to talk about why they're different. Okay, so on the left over here, on the left over here, we are looking at the change in Gibbs free energy for the mixture as a whole, for the whole thing. So this helps us understand the equilibrium conditions. Over here on the right, I am now looking at the change in energy for each reactant molecule or atom as it moves to the product. So this is showing how those reactants molecules react and go through this transition state. So right here's our transition state, this high energy. It's like the barrier, right, that they have to get over. So over here on the right, we're really looking at each individual molecule. We can identify some things. You'll remember we have our activation energy, right? And then we still have our standard Gibbs free energy change. So over here on the left, we're looking at the mixture as a whole, but over here on the right, we're looking at it more individually. If you thought about it over here on the left, you could picture as each of those reactant molecules converted, there'd be this little, for that one molecule, there'd be this little hill, right? We don't see them in that, but that's the idea, that each one of those is going from reactants to products. Whoops, too far there. Maybe, here we go. I get it, guys. Okay. So really here, we just want to look at some definitions because we're going to be looking at these a lot more. So enzymes bring substrates together to form an enzyme substrate complex. The two of them bonded together in some way in a region called the active site. We're going to look at that a lot more. So when we look at these charts, what we see is we've got our uncatalyzed reaction, so no enzyme. And then we have our catalyzed reaction, our enzyme. And what we see is that that hill is smaller, right? I don't really care that you think about those two things. Notice delta G is the same. And this would be the standard Gibbs free energy change. All right, but what we see is that hill becomes smaller, and it's because of this enzyme substrate interaction. All right, one last thing on this video. So let's look at this graph. So on the black line, no enzyme. The pink line, we've got enzyme. And we can see that over in this section, the enzyme makes the reaction rate much faster. But when we get over here, not so much anymore, right? Enzyme, no time. We've achieved the same amount of product. Always good to look at your axes, right? We've got product versus time. So given enough time, we get the same amount of product. So we'll have the same amount of product at equilibrium, the same amount of reactant at equilibrium. And so we're going to have the same equilibrium ratio. Okay? The speed we got there changes, but the equilibrium doesn't. All right, that is it for this video. Next video, we are going to talk about those active sites.